and most of the people sitting here are either their students or students of students. So most of the people are directly or indirectly linked with Professor Zubairy. In arranging summer college, he has been instrumental. He has arranged summer college in 1994, and you can see it was one of the best workshop ever held at INSC. You can see a picture here, Professor Zubairy with Glauber. It is one of the best activities there. Professor Zubairy has been a regular in INSC events. He has been there in every quantum optics event we have arranged here. I think most of the people know about Professor Zubairy. Is not new to them. However, there are some new people, newcomers. So I will give a brief introduction of Professor Zubairy. Professor Zubairy is a university distinguished professor at Texas A&M University, and he is a holder of Munnerlin Heap Chair in quantum optics. He's expert in his research includes quantum optics and laser physics. He has authored several books. The most common books are Quantum Optics, co-authored by Professor Scully, Quantum Optics and Devices, Quantum Mechanics for Beginners, Mysterious Universe. Another book in Urdu, Kainat Ek Hairat Kada. He has been writing articles in Urdu, in Hum Sab blog. These articles are very much common, and people has a lot of interest in reading these articles at website Hum Sab. He is recipient of many honors and awards, which includes William E. Lamb Award for Laser Science in Quantum Optics, Alexander von Humboldt Research Prize, Outstanding Prize Award of OIC, Abdus Salam Prize in Physics, International Khwarizmi Award by President of Iran, Order of Hilal Imtiaz and Sitara Imtiaz by President of Pakistan. He is Fellow of Pakistan Academy of Sciences, American Physical Society, Optical Society of America. Today he'll talk about, his talk is devoted, he has two talks today and tomorrow. These talks are devoted to International Year of Quantum Science and Technology, which has been declared by United Nations this year, has been declared by United Nations as a quantum year, celebrating 100 years of quantum science and technology. So this is the 100th birthday of quantum science and technology. So please welcome Professor Zubairy.
Well, thank you very much, Manzoor, for this nice introduction, very generous introduction. And it's certainly a very great pleasure for me to be back here so often. And it's certainly a great pleasure to be part of this particular Nathiagili Summer School, which is happening at a very auspicious occasion. This is the 100th anniversary of quantum mechanics. As a matter of fact, I was just checking this morning. This is precisely the time, I think we're starting around June 16 till the first week of July, when Heisenberg was in the process of writing the very first paper on quantum mechanics. So this is literally the 100th anniversary of quantum mechanics. My talk today will basically deal with how Heisenberg reached the conclusion that he did. I mean, some part of the story is very well known to almost all of you, but I think I'll try to bring out what prompted Heisenberg to write his paper, which incidentally is one of the most difficult paper to read, is still today. And you will see that towards the end of this talk. So the title of my talk is The Birth of Quantum Mechanics 100 Years Ago. So quantum mechanics, as we all know, happened in two stages. In 1900, the year 1900, basically classical mechanics was almost complete. There was hardly any issue which was unresolved by the laws of classical mechanics. And the laws of classical mechanics were defined by the Newtonian laws for mechanics, and of course, electrodynamics as formulated by Maxwell. And the satisfaction with all these laws was so much that one of the very famous physicists at that time, Lord Kelvin, he's quoted as saying, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." And he could not have been more wrong. Because what happened was that within months, I would say, within of his remarks, the revolution took place, which continues to this day. So at the time of the end of the 19th century, everything could be explained with the Newtonian laws and the laws of electrodynamics as formulated by Maxwell and others. But there were two problems that were still unresolved. One was this radiation emitted by metallic objects, this ultraviolet catastrophe, and the null result of Michelson-Morley experiment. So these were the things which were really still on the horizon, and they both related to light. It turned out that the resolution of the first problem that led to the birth of quantum mechanics, and the resolution of the null result of Michelson-Morley experiment that led to the theory of relativity. And these are the two major theories that have stayed with us for well over 100 years. And it turns out that these theories, after a passage of almost 120 years, more than 100 years, they remain the most successful theories of human history. Very strong statement. But the reason why this statement seems valid is because the precision with which we can make measurements have improved dramatically over the last 100 years. The precision with which we can measure the distances, the temperature, the mass, and so on. But still, there is right now, today, there is absolutely no phenomenon which is in violation with the predictions of these two theories. So this is really quite remarkable. And of course, we all know that these theories have shaped the physics of not just 20th century, but it is still very much involved in shaping the 21st century as well. So this is the conventional sort of old quantum theory, which many of us are familiar with. Some things which happened in 1900 and 1924. As I mentioned, that one of the problems that was unresolved at the end of the 19th century and had remained unresolved for almost 40 years, and that was the spectrum of the radiation radiated by heated metallic objects. I mean, the question was, what was the spectral distribution, the light distribution that is emitted by when we heat a metal as a function of temperature? And this problem was, as a matter of fact, posed by Kirchhoff around 1850, sometimes in 1850s, and had remained unresolved for almost 40 years. It's a very mundane problem. And eventually, Max Planck resolved it, but at a very, very big cost. What Max Planck had to introduce was the notion of the quantization of energy. To be more precise, what Max Planck observed was that if we treat these electrons inside the metal as something like making harmonic motion under the action of incident field, like a swing. Now, when we know about swing, that we give more energy, any amount of energy, any amplitude is possible. It would be very strange to argue that only some amplitudes are allowed and some are disallowed. But this is what precisely Planck did. What he imposed was a quantum condition on how much energy these harmonic oscillators could have. And once he introduced this notion of quantization of energy in there, he could get the right answer. And this was quite remarkable. But of course, Max Planck did not realize at that time the revolutionary nature of this discovery. His feeling still was that, okay, it was a very successful approximation, but perhaps a day will come when it could be explained using the classical ideas of physics. For 5 years, almost nobody noticed this work until Albert Einstein. He wanted to explain the photoelectric effect. Photoelectric effect is basically that you have a metallic object and you shine light on it, and as a result, the electrons from the metal are ejected. The thing which was observed, which was completely counterintuitive, was that for certain colors of light, particularly on the low frequency side, no matter how intense the light beam was, no photoelectrons were emitted. But above a certain frequency, no matter how feeble the light was, electrons were emitted. Now, this was completely contrary to what people knew at that time. And Albert Einstein could explain this phenomenon by introducing the notion of a photon, or a particle, light quanta. He did not invent the word photon. That came almost 20 years later, but he called it light quanta. So he was the first one to deal with the quantum nature of light. So this was like a particle nature of light that he was talking about. And this had the seeds of a very mysterious behavior exhibited by light. I mean, we all knew, for almost 100 years that light behaves like waves in experiments like interference and diffraction. But now we had a phenomenon, photoelectric effect, where the same light was behaving like particles, like photons. Yeah. So this was the beginning of this very, very important notion, which will really dominate the development of quantum mechanics, the wave-particle duality. The third major breakthrough, and this is where I would like to dwell much more in this talk, that came in 1913 when Bohr was trying to explain the structure of hydrogen atom. I mean, it seems very remarkable that at the beginning of the 19th century, the structure of the atom as we know it today did not exist. It was in 1908 when Rutherford came with this notion of nucleus. I mean, nucleus was invented by Rutherford. And his notion was that since atom is supposed to be neutral, so there should be these negative particles, electrons, that should be in orbits around this nucleus, like planets around the sun. But there was no condition on which orbit they could move in. Or Niels Bohr completed his PhD around 1912 or 1913 and ended up as a postdoc to Rutherford. And Rutherford basically gave him this problem of explaining the radiation emitted by hydrogen atoms, something which Rutherford model could not explain. And Bohr could do it, and I'll have more to say about it in a few minutes. So Bohr explained hydrogen spectrum by invoking the quantization condition, which had gone back to Max Planck. Before quantum mechanics was invented in the summer of 1925, one last major breakthrough was made by de Broglie. He was a PhD student in France, And his idea was that if light can sometimes behave like waves, and sometimes they can behave like atoms or particles, uh, uh, particles should also be able to behave like waves. So he introduced this notion of wave-particle duality as applied to particles. Einstein, implicit in Einstein's work was already the wave-particle duality, but with respect to light. So this is the conventional story which is told, which I'm sure most of you are familiar with. Uh, but my intention here is to really see what happened between 1913, when Niels Bohr came up with this quantized notion of hydrogen atom, and 1925. What prompted Heisenberg to introduce quantum theory of basically quantum mechanics, introduce quantum mechanics. Okay, just to complete the story, in 1925, Heisenberg invents quantum mechanics, which is the subject of this talk. And in 1926, Schrödinger presents an alternate formalism, which appeared completely independent of what Heisenberg had done. And this will be tomorrow's talk, what Schrödinger did and why he did it. Okay. But it turned out, actually, Schrödinger himself proved a few months later that the two formalisms were completely equivalent formulations of quantum mechanics. And it turns out that Heisenberg, even though he had the precedence, he introduced it first, but the most popular account for us is that of Schrödinger. As a matter of fact, in many quantum mechanics courses, we do not learn much about what Heisenberg did. Okay, so coming back to the problem at hand. So in the problem that had existed for quite a while, as a matter of fact, going back all to late 19th century, and that was this notion of atomic spectrum. It turned out that each element they gave out its own characteristics spectrum, distribution of colors. For example, this was hydrogen spectrum and carbon and oxygen, and they had a characteristics associated with these elements. So they were like the signatures of these elements. And the question was, how do we understand them from atomic physics? The simplest, of course, was hydrogen atom. Hydrogen atom consisted of just a proton as a nucleus and a single electron surrounding it. So this was a problem that was to be considered. The first person who addressed this problem in a very empirical way was Balmer. He was a high school teacher, never did any research, but at the age of 60, he did something for which he will be perhaps known for a very, very long time. What he observed was that hydrogen atom had some spectral lines. Okay? These are colors corresponding to this wavelength, 410 nanometer wavelength, 434, 486, 656. So here just this data available to him. And what he did was he combined them together into a formula like this. Okay? So that if I substituted n equal to 3, then I got this line, 656 nanometers. If I put n equal to 4, then I get 486 nanometer line, and so on. Okay, so just this empirical observation, 4 numbers, how do they fit into a formula? And this was quite remarkable, very simple, but really something that people noticed. And now the question was, how do we derive it from a microscopic model or theory? So this was the problem. As I mentioned, Balmer in his lifetime wrote only 2 papers. One was just this. He took these 4 numbers and placed them into a formula. And I think the second paper was that he was told that there are not just 4 lines, but many more lines, and he fitted them with his formula. But very soon it was realized that in hydrogen atom, and please remember this thing, we are talking about hydrogen atom only. What was realized was that there were many other lines. As a matter of fact, there were these groups of lines which are here and here and so on. And these have different names associated with them, with the discoverers, Lyman, Balmer, Bastian, and Rydberg was the one in 1988 who combined all these different lines in terms of a formula which is very similar to like Balmer formula, but now it has two numbers, one describing as which series we are talking about, and the other one corresponded to what line we are talking about within that series. Okay, so this was again completely empirical. There were these numbers, and what formula did they satisfy? But the challenge was to develop a theory. How could these numbers be obtained from a theoretical argument? Of course, Newtonian mechanics or Maxwellian electrodynamics was unable to explain any of this. Even Niels Bohr, even Rutherford could not explain the spectrum of the simplest of the atoms, hydrogen atom. Well, Bohr was the first one who really could derive all these spectral lines by invoking a quantum condition. Okay, so basically his model was like this, that electrons, they are moving in orbits around the nucleus, in fixed orbits, and he called them the energy levels. And the level with the least energy is the one closest to the nucleus. And as we go farther away from the nucleus, the levels have more and more energy. And the thing that we assumed was that these electrons can jump from one energy level to the another one. And in that process, if they are going from the lower energy to the higher energy, they would absorb. And in the case when they are jumping from up to down, they would emit energy. So this was the model that Bohr proposed. But this was not all. This was not all. I mean, Bohr's object, of course, was derive this Rydberg formula, the spectral distribution of the radiation emitted by the hydrogen atom. So he considered this model where single electron moving in these orbits. There were, for an electron orbiting around a proton, there is the centripetal force, which is provided by this Coulomb force. So this is the classical formula. The second formula, which again is completely classical, and that is that the sum of the energy in any particular level that corresponded to the kinetic energy plus the potential energy. No big surprise here. But but Bohr postulated, and this was only Bohr could do it, because it was like imposing a condition for these orbits, stable orbits, and that is that only those orbits are allowed where the angular momentum is an integral multiple of the Planck's constant. Now, this is something which Bohr just imposed to get the correct result. There was no justification for it. And once he did that and included this Einstein's relation, he could get the correct result. Rydberg, Rydberg formula up to the numbers, very precise numbers. And this was almost the exact formula. This postulate was able to do that. So this was a big success. Hydrogen atom was now explained. But then the question was, what about others? Can we apply it for helium? Can we apply for carbon and so on? And then there were these other problems, like if we apply a magnetic field or electric field, these levels are shifted. Can this kind of formalism explain all of that? Well, it turns out that there was only partial success, but not complete success. The most important thing was there was no theory. There was no Newtonian type equations or Maxwell's type equation. It was just postulates. You do one postulate to explain one thing, then another postulate for another thing, and so on, so on. So this is the situation that existed in 2013. And this situation continued to exist until 2025, 12 years. So for 12 years, newer and newer phenomena were being discovered, which could not be explained by the classical mechanics of Newton and Maxwell. So now, and there was no theory. So this was really a period of a very major crisis in physics, how to explain, how to develop a theory. Okay, so the first step, so now what I will be doing in next half an hour or so is to give you some notions where there was success and then some ideas where there was a failure, such that at the end, Heisenberg would come and there was light again. So the first observation after Bohr's work was by Stark shift. We all know about it. But what it was that if we apply when atomic hydrogen is exposed to a static electric field, then the spectral lines shift. So for example, these are the lines. And now if I apply the electric field, then the energy basically shifts. But it is not just the shift splitting. It is not just the shift, but it is also the splitting more and more. So each single line that we talked about, which Bohr could explain, became multiple lines. Okay? So as the electric field is increased, there are these multiple lines. And how does that come about? Okay? So static electric field, spectral lines split, and the amount of splitting was proportional to the electric field strength. This was the linear Stark effect. So this was already in 1913. And the persons who explained it were these two persons. One of them was Epstein, a Sommerfeld PhD student. Sommerfeld, by the way, I don't know how much is known here. There are two persons in the foundation, in the birth of quantum mechanics, who never received the kind of recognition that they deserve. And one of them was Sommerfeld. The second one also I'll mention in a while. I mean, Sommerfeld really he was the thesis advisor, by the way, PhD thesis advisor of both Heisenberg and Pauli. And he was nominated for Nobel Prize, I think, almost 30 years in a row, but never got it. Paul Epstein was Sommerfeld's PhD student, and Schwarzschild, those who are familiar with relativity would know this name instantly. He was the first one who solved Einstein's equations of relativity and predicted black holes, etc. So they both actually came up and they explained this linear Stark effect that I talked about. And this became one of the very rare instances where Bohr's formulation, this old quantum theory as we call it now, could be solved exactly and give the correct results. But it turns out that in this case, as we could imagine, since each line was split into multiple lines, so there was not just one quantum number, n. N was, these different orbits that Bohr had talked about, but there were two quantum numbers, n and l. And they were excellent agreement with experiments. And Stark would win the Nobel Prize very soon. As a matter of fact, ironically, he got the Nobel Prize before Bohr got his prize. But he had done the experiment, so that's probably the reason. So Bohr's theory of hydrogen atom, the energy was given by just this one quantum number n, which represented these energy levels. But now, what Stark had shown was that they become highly degenerate, especially when we apply the this electric field, and to each n belongs several states corresponding to these orbital quantum number L. All of them are degenerate, and this degeneracy is removed by the application of the electric field. Then we can see these different levels. So N and L, in general, several states with distinct magnetic quantum, all of it, and so on. So it turned out that, as a matter of fact, this was a Stark effect, but then what was shown was that for each N and L belong in general several other states with distinct magnetic quantum number, and that would be manifested if the magnetic field is applied. And then for N, L, and M, there were two states labeled by spin, and they were again degenerate. So now, and relativistic effects were needed to really lift this degeneracy and explain the entire fine structure of the spectrum, including all these relativistic effects. So all this could be done within the context of this old quantum theory. This is all happening before quantum mechanics was born in 1925. So a lot of progress was made. So external magnetic field lifts the degeneracies in magnetic quantum number and the spin quantum number. And this was the Zeeman effect. There is Zeeman. And all the anomalies could be explained. And then all these four quantum number of the modern atomic spectroscopy, N, L, M, and S, they had been employed already within the context of the old quantum theory. And remarkably, and this is something which is not appreciated very much, Pauli's exclusion principle. Wolfgang Pauli came up with an exclusion principle where he argued that no two electrons in hydrogen atom could occupy the same, all four same quantum number. So each electron could have only one set of these numbers, and so on. And this was also formulated before the birth of quantum mechanics. But Pauli would get recognition of it long time afterwards. I think he got the Nobel Prize in 1945 for this work. Okay, so here is sort of the summary of this spectroscopy, that there were these quantum numbers N, L, M, and S. Typically, they are degenerate. In Bohr's work, there was just N, and then Stark effect, and then Zeeman effect, and relativistic effects. So everything was known about atomic spectroscopy, but for hydrogen atom only. Hydrogen atom, in some sense, is a gift of nature, because it turns out that hydrogen atom could be solved exactly by Niels Bohr, theoretically, and then those results could be compared with the experiments. When quantum mechanics came along, Schrödinger equation, as you know in your quantum mechanics courses, this is the only problem to this date, 100 years later. This is the only real problem that can be solved exactly via Schrödinger equation. No other real problem. I mean, there are models, harmonic oscillator and so on, but there is no real problem other than hydrogen atom, which can be solved exactly. You need numerics to do that. And very surprisingly, when the relativistic quantum mechanics was written by Dirac equation, this was also hydrogen atom was the only problem to this date which could be solved exactly. So nature had given us sort of a ruler that, okay, here is something where the quantum, where the exact solution, theoretically, one can find the exact solution to any decimal point that you want to and compare it with the experiment. So, that played a very important role in the development of the physics of the 20th century, hydrogen atom. Okay, one work which fascinates me personally a lot, and that is that how Sommerfeld, so this is what Bohr had done. This is what Bohr had done through his ansatz or assumption that angular momentum of this electron should be integral multiple of the Planck's constant. Okay? So then he got this result. But it turned out that Sommerfeld applied relativity. I mean, relativity was developed completely independently of quantum mechanics. But it turned out that Sommerfeld could apply this relativistic invariance arguments to really get this energy, which included all the relativistic effects. And it turned out that many, many years later, around 1927 or 28, when Paul Dirac wrote down the equation, the relativistic quantum equation, it turned out that the solution of this equation was exactly this, just like this became the solution of the Schrödinger equation. So this is quite remarkable that Sommerfeld, by using some very hand-waving kind of arguments, could get the exact result. Okay? So this was the brilliance of Sommerfeld. As I say, he remains, in my mind, rather unappreciated for some of these things. So now the situation in around 1924 or 25, at the dawn of quantum mechanics, was like this, that this old quantum theory, the founders were Planck, Einstein, and then Niels Bohr, that could explain a lot of things. It could, for example, talk about quantum numbers, as we have talked about. It could talk about selection rules, which transitions are allowed and which are forbidden. They could do that. Pauli wrote down his exclusion principle without any recourse to the quantum mechanics. First steps towards quantum chemistry was taken. How these different atoms can combine together, what is the mechanism that will be involved. So the first steps were, but not complete details. Covalent bonds and ionic bonds and so on, they came much later, once a full understanding of atoms was understood. Quantum statistics, some basic ideas of quantum statistics were there. I don't have time here to mention, but what I'm talking about are these Bose-Einstein statistics and Fermi-Dirac statistics. The basic seeds were already there in 1924 already. But then there were some amazing failures of old quantum theory. It could not explain anything about helium, the next simplest atom. And of course, higher elements like carbon, oxygen, and so on, they were completely intractable. Nothing could be known about them. Nonlinear Stark effect. If you increase the field very intense, then this increase is not directly proportional. This separation of these energy levels is not directly proportional to the electric field applied, but it changes nonlinearly, and that could not be explained. And most importantly, wave-particle duality. How is it that this same light, which is coming in here, I take this light and do an interference experiment, then it behaves like waves. It cannot be, if I treat this light as consisting of photons, that experiment cannot be explained. And I take the same light and do the photoelectric effect, then it would behave like particles. How come? When does it decide? At what point does it decide it has to behave like waves and particles? So these are the questions, very fundamental questions, and some of these questions stay with us till today, and maybe tomorrow I'll have something to say about that. Okay. So these were the failures. Okay. So now something needed to be done. A quantum mechanics somehow had to be invented. There was another very serious problem, which became the reason for Heisenberg to invent the quantum mechanics. And that is that this notion of the classical theory of dispersion, which goes back to 1870. And the whole idea is that if I take an atom or atomic system, I shine light upon it, this light is absorbed and then re-emitted. So how does that happen? So what are the frequencies? How this incident light of a certain frequency, and when it is irradiated, on an atom, then atom emits radiation. And the question was, what frequency does it radiate? So that was really the problem. Bohr had solved it by talking about these transition frequencies. But classically, the only frequency in the problem, if you think about it, is the rate at which the electron is rotating around the nucleus. That's the only frequency in the system. Where does these Bohr frequencies come in, these transition frequencies? So that was a problem which really bothered some people. And this was the problem that Hendrik Kramers addressed. He is the second person, and just like Sommerfeld, he is again one of the most unappreciated person, in the sense that actually somebody was counted. He wrote the most crucial and most important paper in 9 instances before the major discovery was made. So, I mean, Kramer's work really motivated Heisenberg to do his work. And there are many other instances where Kramer's was right there, but he did not cross the line. So never got the Nobel Prize and never got the kind of recognition that he deserved. So Kramer's realized this to be a big problem, that when you want to talk about this dispersion, how do you incorporate Bohr's transition frequencies into the problem, when the only frequency that is known to us in classical mechanics is the orbital frequency. Okay? But orbital frequency has no place in this analysis. So, I mean, this problem was becoming more and more obvious. And in February 1924, Pauli wrote to Bohr, the most important question seems to me to be this: to what extent may definite orbits of electrons in the stationary states be spoken of at all? So now there was this idea, are these orbits that Bohr had talked about, okay, orbits of electrons around the nucleus, like the orbits of the planets around the sun, how real they are? I mean, Bohr had just postulated it. He did not prove by any means. But now the question was, what is the nature of these orbits? I believe that this can in no way be assumed as self-evident. Heisenberg has, in my view, and this really is where Heisenberg now starts getting in, has, in my view, precisely hit the mark on this point, in that he doubts the possibility of speaking of definite orbits. So Heisenberg, as we are going to see, really starts doubting about this orbital picture, that the electrons are really in very well-defined orbits, as Bohr had postulated. This should not make any sense, because this could not explain, for example, this dispersion type relations. Pauli also wrote to Sommerfeld, the model concepts that is the use of orbits are now in a severe fundamental crisis, which I believe will finally end with a further radical sharpening of the contrast between classical and quantum theory. So Pauli and Heisenberg and many others were realizing that this notion of orbits really is not tenable. And he writes to Bohr, not only the dynamical concepts of force, but also the kinematical concept of motion in the classical theory must undergo profound modifications. And therefore, he avoided the term orbit altogether in his paper on Zeeman effect. So this notion of orbits is really under discussion. Enter Kramers. Okay, Kramer dealt with this problem of dispersion of light. He wrote 2 papers in 1924. One was written by himself, on this problem. And in the second paper, so he was actually an assistant to Niels Bohr in Copenhagen at that time when he wrote these two very important papers. And Heisenberg has also joined Bohr in Copenhagen as his assistant. So now Heisenberg was in some sense an assistant to Kramers, who was himself an assistant to Niels Bohr. So this is how the chain worked. And Kramers was really one of the brightest lights there at the institute. And in the second paper, he included Heisenberg as a co-author. Heisenberg himself gave full credit of that work to Kramers. So Kramers' work deals with the dispersion of light, emission of secondary light by an atom exposed to and excited by a light beam. So this was the problem. And these were the two papers I talked about. Yeah. Max Born would say about this contribution. Max Born, incidentally, I mean, of all these people, Max Born was the boss at that time of Heisenberg in Göttingen. So Heisenberg was working for Max Born, but he was visiting Niels Bohr and to Niels Bohr at that time. So it was the first step from the bright realm of classical mechanics into the still dark and unexplored work of the new quantum mechanics. And the first words, first time anybody used the word quantum mechanics was Max Born, who incidentally happens to be my intellectual grandfather. My PhD thesis advisor, Emil Wolf, was also an assistant to Max Born. Okay, so just to give you an idea, if one does the classical theory of dispersion, this is the kind of equation you will write down. I mean, this is, forget about this middle term, which corresponds to the damping, energy loss. But this is like this harmonic oscillator motion, this term and this term, which is driven by the applied electric field. Okay? But the thing about it is that this omega naught would correspond to the angular frequency of the oscillating electron. So in the classical picture of dispersion, it was the oscillating frequency of the electron, which was there. And one could derive these expressions for the induced dipole moment, etc., in terms of this orbital frequency of the electron. This kind of frequency did not exist in Bohr's old quantum mechanics. Okay? There was this energy levels, energy frequencies associated with the energy levels. Kramers' work, very sophisticated. Essentially what he did was he used these correspondence principle that if you go to higher quantum numbers, then the system becomes more and more classical. He used some of these arguments that higher quantum number, then the orbit picture becomes more realistic, but at low quantum number, there is no such thing in here. So using these ideas, Kramer could get a dispersion relation. And then this was the work, part of this work he published jointly with Heisenberg. So this was sort of the work which made Heisenberg ready to make the jump. So now Heisenberg comes into picture. So Heisenberg was a student of Sommerfeld in Munich, and he first met Niels Bohr at a meeting in Göttingen in the Institute of Max Born. He visited as a very young person. Heisenberg visited there in Göttingen, which was essentially a celebration for Niels Bohr, big scientist, 1922. And there, Bohr and Heisenberg apparently had a very, they had a lot of discussions. They went for long hikes and so on. And so essentially Heisenberg became, with the problems of the quantum mechanics, with his interaction with Niels Bohr in the institute at Göttingen, And Bohr invited Heisenberg to visit him in Copenhagen. And following these discussions, Heisenberg now wanted to develop a full-fledged theory. But it turned out that he had a severe attack of hay fever, and he had to leave. And he basically went to this island, Heligoland, where there is not a drop of leaves. There is no leaves. It's a bare island. Okay. In the summer of 1925, and that was where he conceived the basis of quantum theory. So this is that island. But here somehow you see a lot of greenery, but apparently there was nothing green in here, and Heisenberg sat there. So this was sort of his description, that it was about 3 o'clock at night when the final results of the calculation lay before me, and so on, and so on. So this probably must be the scene when the sun was rising. Okay, this is the title of his paper. This is the title of his paper. This is in English: Quantum Theoretical Reinterpretation of Kinematics and Mechanical Relations. And the first sentence, which in German is given here, this is what he said. And this is a very historical sentence which haunts us to this day. The present paper seeks to establish a basis for theoretical quantum mechanics founded exclusively upon relationships between quantities which are in principle observable. And what does he mean by that? Basically, as we have just seen, I mean, what Heisenberg was very uncomfortable with was with this notion of the orbit, which was very central to Bohr's formulation of quantum mechanics. What he argued was that an orbit is not an observable quantity. And when I throw a ball, you would say, well, it follows a trajectory. But that trajectory by itself is not observable. You can basically infer the trajectory by making a measurement at each point, this point, this point, this point, and so on, and then construct the trajectory. Trajectory by itself is unobservable quantity. So Heisenberg's point of view was that quantum mechanics should be formulated only in terms of the real quantities that can be observed rather than on abstract concepts like trajectories. So this is essentially what he's saying here. So he starts by arguing that even for the simplest quantum theoretical problems, the validity of classical mechanics cannot be maintained. And the simplest problem that he was considering was not hydrogen atom problem. As a matter of fact, he did not solve the hydrogen atom problem. That was solved by Pauli many months later, and by Dirac. That is another very interesting story which I won't be able. So Heisenberg is not but it turns out that what Heisenberg was doing, and to this day, people have tried to read his paper, and it is not clear exactly what he was trying to do, but he got the right result. Okay. How much time do I have left? Oh, 5 minutes. Okay. Okay, so in one dimension, we have a classical orbit, and a classical orbit is defined by x of t. This we all know. We solve Newton's equations, F is equal to ma. That gives us what is the value of the position at a given time. Similarly, how fast the object is moving at a given time. Okay. So this was what was known, but Heisenberg now is taking inspiration from his work with Kramers, which was essentially Kramers' work. So basically, Kramers, what he had argued was I mean, when they were looking for the scattering of this light from the atoms to give an output light, there were these amplitudes for depending upon the frequency, how much amplitude for a given frequency that will obtain. But they had, as a matter of fact, introduced this notion. It would depend on the transition from the atomic state N to atomic state M. These are the same states that Bohr had talked about, that you go from one state to another, N state to M state. And he used this symbol. Okay? So this was what Kramer had done, what Kramers and Heisenberg had done. Now Heisenberg takes the jump, okay? And nobody knows why. And what he reasoned was, let's try to do something similar for the position. So for amplitude, it was fine. How much light is emitted for a given frequency when you jump from this level to this level. But now what he was arguing was, let's do it for the position as well, and for velocity as well. So let's, instead of representing by x of t, let's represent it by a quantum type symbol with m and n here. It would appear very opaque to us at this point why he would say something like that. Only he knew why he was saying that. So m and n refer to the quantum states of the harmonic oscillator. Okay. There were two possibilities. M was equal to n, so this would represent the coordinate at a time t when the system was in the state n. So this is how he argued. But of course, when m was not equal to n, then it would represent some kind of a transition from coordinate from state m to n. Classically, it's very difficult for us to even visualize what it means. But this is what Heisenberg argued. Similarly, he said the same thing about the velocity, that instead of talking about velocity as something like an ordinary quantity, it should be represented by this sort of element m and n. Okay, and these these are the quantities which in Heisenberg's criterion are observable quantities. But very soon he realized there was a problem. Okay? And the problem was that what about the energy? What about the energy of the particle in a state n? Okay. So now he has to take the classical expression for the energy, which is like x square, half mv square, or half omega square x square. Okay. How do you define x square? X you can define as x m n, but what about x square? Okay. So this was the first difficulty that he encountered. And basically what he argued was that x square mn, it should look something like this. So x goes like, has these elements mk and kn, and it should be sum over k. Okay. So this is how he defined x square. Okay. And now I think almost everyone in this room would recognize what it is. But Heisenberg in 1925 did not. It is just matrix multiplication. But Heisenberg did not have enough mathematical background to see that. Okay, but then there was another problem now. You can do that, but now the other problem was that when he tried to consider two such quantities, like x and y, okay, so when you take the product of them, then you can do exactly what was done before. But the problem was that if you multiplied x with y and got it, it was not equal to y times x. Matrix multiplication is not commutative. xy is not equal to yx. So this was a big problem for Heisenberg. Okay. Now, what about energy? So the whole name of the game was energy. Can we get the spectrum, the energy spectrum? Bohr had gotten energy spectrum using his arguments and so on and so on. But now this new quantum mechanics, could it give us the correct value for the energy? And energy, he argued, was that it should satisfy certain criteria such that it should be diagonal, H and N. HMN should be equal to 0 because H is a scalar quantity. It has no transition. It is some actual value. So it should be, should not depend upon time. Conservation laws built in there. It should be HMN should be 0 when M is unequal to N. And En should be quantized, okay, along the lines of Bohr quantization. And it turned out that he could prove all these things in his formulation, which he was doing only for harmonic oscillator. He was not addressing the problem of hydrogen atom. That was too complicated for him, frankly speaking. So on so this was the summer of 1925 when Heisenberg was working in Heligoland. On 19th June, he returned back to Göttingen, where he was based at that time. 9th July, he finished writing up his results. Then he gave this paper to Max Born, his boss at that time, the director of the institute, Max Born, and basically asking him to read it over, and if he liked it, send it for publication, and went on his vacations. And then he came back in August, and by that time he had realized that he had done a major breakthrough. And the persons who really explained it, everything, I mean, what Heisenberg's paper, if you try to read it even today, it's completely opaque, very hard to understand what he's trying to do and why he's trying to do it. But what happened was that when he gave his paper to Max Born realized the importance of it. But what he did was he now wanted to work it out in details by himself. And he needed a student. He asked Pauli to join him. Pauli, being a very proud person, refused to join Max Born in this effort. So then he asked Jordan to join him. So Born and Jordan wrote the second paper where they tried to explain what Heisenberg had done. And they recognized for the first time that what he was doing was matrix mechanics. What this notion of XMN and the multiplication rules, etc., those were the same rules that are obeyed by matrix mechanics. Born had a very good training of mathematics. He was a student of perhaps the, let me see, Hilbert. He was a student of Hilbert. If there was time, I could tell you some stories about Hilbert, how great a mathematician he was. So Born realized what Heisenberg was doing. And then when Heisenberg returned, then the three of them, Born, Jordan, and Heisenberg, wrote a very famous paper with complete details, and it is called three-man paper to this day, where they worked it out. So this is the recollection of Max Born, that when Heisenberg gave his paper to Max Born, so according to Max Born, Heisenberg told him that he had written a crazy paper and did not dare send it in for publication. And he asked Born to read it, and if he liked it, sent it to Zeitschrift for Physics. And once Born read it, he became enthusiastic, began to think about it, and he realized that this multiplication law must have a meaning. And then he realized that this multiplication was nothing but the matrix calculus, which he had known for a very long time. So then he interacted with Pascal Jordan. And then, of course, there was another paper, as I mentioned. Okay. Is my time up? Okay, so let me actually skip some part. Okay, so this is this paper by Born and Jordan, perhaps not visible from far away. And this is the other paper by Bohr, Heisenberg, and Jordan. Bohr somehow did not get appropriate recognition for the invention of quantum mechanics. And that was for a very sad but political reason. And that is that Bohr's contributions to the foundations of quantum mechanics were all tied with Jordan. And Jordan was an avowed Nazi, very, I think he was like a member of the Nazi party under Hitler. And soon Hitler came into power, and the Nobel Committee, for example, did not want to recognize an avowed Nazi. And Bohr could not have been given credit without giving credit to Jordan. And therefore, Bohr had to wait for a long time until 1950s for his recognition when he won the Nobel Prize. But let me actually just, let me see. So yeah, Bohr and Schur. So let me actually get to the last part. Maybe I'll come back to these equations tomorrow. But just to show you that what Heisenberg did, how incomprehensible it was. So one of the greatest physicists of our generation, he passed away only 2 or 3 years ago, Steven Weinberg. He said something like this, that if the reader is mystified at what Heisenberg was doing, he or she is not alone. I have tried several times to read the paper that Heisenberg wrote on returning from Heligoland. And although I think I understand quantum mechanics, I have never understood Heisenberg's motivations for the mathematical steps in his papers, the ones that I mentioned. Theoretical physicists in their most successful work tend to play one of two roles. They are either sages or magicians. It is usually not difficult to understand the papers of the sage physicists, clever physicists. But the papers of magician physicists are often incomprehensible. In this sense, in that sense, Heisenberg's 1925 paper was pure magic. Perhaps we should not look too closely at Heisenberg's first paper. So this in some sense encapsulates, Heisenberg's original work, which he himself really did not appreciate the meaning and the significance of that work until Max Born and Jordan and Dirac, and to some extent Pauli, they really came along and explained it. So I think I'll quit at this point and continue some of this discussion tomorrow. Thank you.
Using quantum mechanics.
Mhm.
But you mentioned Pauli proposed this Pauli exclusion principle before quantum mechanics. He postulated it, or there is some theory behind it?
Okay, so the thing was that the question is, Pauli introduced his exclusion principle before the birth of quantum mechanics. And how come? How come well, the thing is, as I tried to explain, one thing which was very well understood were these quantum numbers and the selection rules, especially for hydrogen atom. So these were very well known, and basically Pauli could sift through these rules to formulate this principle. So he didn't need a Schrödinger equation or Heisenberg's formulation to do that. Yeah, spectroscopy really developed to quite an extent before quantum mechanics was eventually born. Pardon?
Based on the selection rule.
Based essentially on selection rules, yes.
Thanks, Manzoor sir. Now, our next speaker is Kadir Durak. Dr. Kadir Durak is an assistant professor in the electrical and electronics department at A&M University, Istanbul, Turkey. He obtained his BS in physics from Middle East Technical University in 2009 and completed his PhD in physics at the National University of Singapore in 2015. Following his doctorate, he worked for 2 years at the Center of Quantum Technologies, where he led a research group developing space-to-ground quantum key distribution via QVSat. His research interests include quantum cryptography, quantum information, photonics, and quantum electrodynamics, with a particular focus on entangled photon sources, secure communication protocols, single atom photon interaction, and quantum teleportation. Today, he will deliver 2 lectures. His first lecture, the title of this lecture is Quantum Key Distribution and Post-Quantum Cryptography, Security Realities in Quantum Era. This is the title of his talk. Please welcome Dr. Kadir Durak.
Thank you very much. First of all, thank you for I would like to thank the organizers for inviting me again. So I think this is my 4th time in this conference series. And it's so nice to see that we are at the 50th year of this organization. Yeah. 50th year of the Natyagali Summer College. So today I will talk about quantum key distribution and post-quantum cryptography, but mostly